Enamel is the hardest tissue in the body. Due to this extreme density, it's widely assumed to act as the primary reservoir for fluoride. That assumption is incorrect. Of all the mineralized tissues in the dental anatomy, cementum actually holds the highest concentration of fluoride. This data table compares the distribution of fluoride across the structures. While the enamel surface caps out at 2,000 parts per million, mature cementum sits securely at the top of the hierarchy. Through continuous accumulation, cementum reaches concentrations of up to 6,000 parts per million. To understand how a thin, seemingly fragile root coating becomes the body's ultimate fluoride sink, we have to track its entire developmental lifespan. Cementum's clinical utility is driven entirely by its unique ectomesenchymal origins and a lifelong process of chemical substitution. The process begins embryologically. Cementum originates from the dental follicle, a structure derived entirely from migrating neural crest cells. These neural crest cells differentiate into a specific type of embryonic connective tissue called ectomesenchyme, which clusters to form the dental follicle surrounding the tooth germ. This cross-section shows Hertwig's epithelial root sheath, or HERS, acting as a continuous barrier between outer follicle cells and inner dentin. HERS soon undergoes fenestration, physically breaking apart. These new gaps allow outer follicle cells to migrate through and contact exposed root dentin. Warning tone. A frequent trap on board exams is the claim that HERS cells themselves form cementum. They do not. HERS strictly acts as an inducer. It is the physical contact with the dentin that triggers the follicle cells to begin differentiating. This sequential diagram illustrates stage 1 of cementogenesis. The newly attached dental follicle cells undergo morphological changes, transforming into plump, cuboidal cells called cementoblasts. In both their cuboidal structure and their matrix-secreting function, these cementoblasts are directly analogous to osteoblasts in bone formation. In stage 2, these cementoblasts begin secreting a dense organic matrix directly onto the dentin border. This initial unmineralized layer is called cementoid. The cementoid matrix is composed primarily of type 1 collagen, acting as intrinsic fibers, alongside complex proteoglycans and glycoproteins. It also contains highly specific non-collagenous proteins, namely osteopontin, bone sialoprotein, and osteocalcin. This precise mixture of organic proteins establishes the essential structural scaffolding. Without it, the subsequent phase of mineralization cannot occur. In stage 3, the unmineralized cementoid hardens as hydroxyapatite crystals deposit onto the protein scaffold. This mineralization front is highly directional, advancing steadily outward from the dentin surface. Extrinsic collagen bundles from the periodontal ligament, Sharpie's fibers, penetrate the advancing boundary and become physically locked within the matrix. Stage 4 defines the final architectural layout of the tissue by dictating the fate of the cementoblasts themselves. As the matrix rapidly mineralizes during the formation of cellular cementum, some active cementoblasts fail to retreat, becoming physically trapped within their own secretions. Once entrapped, these cells are reclassified as cementocytes, resting permanently within hollow microscopic spaces called lacunae. Much like osteocytes, these cementocytes remain connected, communicating with one another through a complex network of tiny canals known as canaliculi. This creates a strict viability gradient. Cementocytes located close to the outer surface remain well-nourished and highly active, while those trapped deeper within the matrix gradually degenerate and die. The rapid, self-entrapping nature of cellular cementogenesis leaves behind a highly porous organic foundation. It is this exact porosity that primes the tissue for chemical substitution, which brings us back to the anomaly from the beginning of our analysis, how this newly formed tissue climbs to an astonishing 6,000 parts per million of fluoride. The first two variables are environmental. Cementum is deposited continuously throughout a person's life, and its outer surface remains in constant direct contact with fluoride-rich periodontal ligament fluid. The next two variables are structural. Cementum mineralizes at a relatively slow rate, providing ample time for chemical integration, and the root itself presents a massive surface area to volume ratio, maximizing exposure. Looking at this 3D molecular model of a hydroxyapatite crystal lattice, we observe the precise mechanism of incorporation. Environmental fluoride ions physically substitute into the lattice, displacing the hydroxyl groups. This one-for-one ionic swap alters the compound, resulting in the formation of fluoroapatite. Fluoroapatite requires a much lower pH to dissolve. By replacing the hydroxyl groups with fluoride, the root surface physically transforms into a highly acid-resistant shield. Because this chemical substitution occurs primarily through surface exposure, the fluoride incorporation is not uniform throughout the cementum layer. This gradient map demonstrates the strict spatial distribution. Fluoride levels peak at the outermost surface, dropping to moderate levels, and are lowest near the dentin. Vertically, apical cementum at the root tip holds significantly higher concentrations than the cervical cementum. This porous organic matrix is why clinical topical fluoride applications penetrate cementum much more readily than they penetrate the dense, highly mineralized enamel. Clinically, this resulting layer of fluoroapatite provides critical resistance against root caries. It is also the specific mechanism we rely on to reinforce exposed root surfaces when treating patient sensitivity. Forensically, because cementum adds unresorbed layers continuously year after year, it operates as a permanent biological biomarker. Pathologists read these distinct layers to estimate a patient's age and trace their historical environmental fluoride exposure. The entire lifespan of the root functions as a chronological record of continuous chemical fortification. Understanding the embryology and the chemistry of this process culminates in a single, highly testable hierarchy of dental hard tissues. This typography displays the definitive rank order of fluoride concentration. From highest to lowest, cementum, followed by the enamel surface, bone, dentin, and inner enamel. Memorizing this precise ranking is a mandatory requirement for mastering oral biology and passing clinical board exams. While the crown's enamel handles mechanical stress of mastication, it is the porous, cellularly entrapped cementum that serves as the body's ultimate lifelong chemical fortress.